Hi, Grandpa Dave here with my grandson David, and I was just tuning my guitar using my smartphone app. The CFS doesn't have an app for that, does it, David?
It don't news.
It doesn't, but it does have over a dozen open source apps that can meet a good chunk of your mission's functionality. I've broken these apps into groups, and today this tutorial will be talking about what I call the Runtime apps. These are apps that provide services that are needed by every app in the system. You ready to do this, David?
Okay.
Let's do it. The software bus goes pen and gold.
We have OpenSat Kit's main screen showing, and the middle section of the first tab contains links to application groups. I've selected the Runtime Environment button. I've grouped Command Ingest, Scheduler, and Telemetry Output as the Runtime Environment apps because every app depends on these three apps to provide an operational environment. Other apps such as File Manager are needed in a complete flight system but are not required from an app runtime perspective. NASA has 3 versions of these runtime apps, and they include it in the CFS bundle, but OpenSat Kit has its own version that I'll explain later why. On the right side, there's a panel, and there's access to each of the app's commands, telemetry, and tables. The next section is links to functional screens. The Manage Runtime app screen provides quick access to the commands and telemetry for changing and displaying table entries. For example, I'm going to send the scheduler message table to send an entry telemetry for entry 617. And as you notice, the top row is the message scheduler table, and we just got index 17, and it displays the entry. The second row is the scheduler table, and this command is smart enough that it goes back to the scheduler table to see which entry uses the message table. And if it didn't, if there's not an entry, it just wouldn't display. And the third row is the KitTO packet table entries. And the last 2 entries are the statistics that are taken from the TitKio's housekeeping package. Down here are convenience to some of the commands for loading and dumping tables and also doing what I just did with the entries. And we'll be looking at this more in that tutorial. Going back to the previous screen, the last section contains some learning resources. There's access to some demo training scripts that we'll be using later on in the tutorial. There's also access to this training video on YouTube, as well as the full slide deck. In this tutorial, I'll provide an overview of the Runtime apps, describe how to integrate an app with the Runtime apps, provide guidelines for designing a scheduler-based system, and discuss different runtime environments during a mission's lifecycle. In a future video, I'll discuss transitioning from OpenSat Kit to Flight, which is really about implementing additional CCSDS standards in the Command Ingest and Telemetry Output apps. Applications need a way to interface with the ground system. Command Ingest, or CI, accepts commands from the ground system and sends them on the software bus. Telemetry Output, or TO, reads messages from the software bus and sends them to the ground system. Some versions of TO have a packet filtering mechanism that allows the downlink data rate to be controlled. There are actually multiple versions of these apps because different environments may require different features. The CI and TO apps used in some test environments may not be the same as those used in flight. UDP is a common protocol between the lab versions of CI and TO and the ground system. I have created versions specifically for OpenSat Kit because I wanted to use text tables that could easily be manipulated by tools. The KitTO app includes a packet filtering feature that I'll demonstrate later. No flight versions of CI and TO have been released due to ITAR restrictions. Note that a CFS startup script defines which apps are loaded during initialization, so it's easy to load different versions of CI and TO on different platforms. Here's a look at OSK's KitTO packet filter table. It's an array of packet objects. When a packet table is loaded, KitTO subscribes to receive each packet on the software bus using the attributes provided in the table: priority, reliability, and buffer limit. Each packet has a filter associated with it that allows n of x packets starting at offset O to be sent. This filter can be applied to the packet sequence count, type 2, or the packet time, type 3. This is the same algorithm defined in the CFS utils library and used by the data storage app. The Scheduler app provides a means to coordinate and schedule applications, allowing developers to create a synchronized flight software system. A synchronized system helps with load balancing, meeting real-time deadlines, test repeatability, and system diagnostics. The scheduler app is not to be confused with the underlying operating system scheduler. However, the application task priorities and the scheduler app schedule must be designed to complement one another so the overall system goals will be met. Now we'll take a look at the scheduler and message tables. The schedule table is divided into slots, and the first slot is typically synchronized with a 1 Hz clock. The number of slots is configurable. Each slot can contain multiple activities, and the number of activities per slot is also configurable. A flight mission with a 10 Hz attitude control law may have 100 slots, so the system designers have 10 slots to work with for each 100 millisecond control cycle. An activity results in a message being sent on the software bus. Here's an excerpt from Kit Scheduler's JSON schedule table. I've highlighted the limit checker's execution entry. When limit checker or LC receives this message, it samples its action points. It's okay if you're not familiar with limit checker. What's important is that you understand limit checker uses the scheduler as the mechanism to control its execution. The activity definition includes the name of the activity, an optional description, the index, so in this case it's slot 1, activity 0. The initial state can either be enabled or disabled. For limit checker, it's initially disabled because it monitors system states, and during initialization the system may be noisy. Limit checker could be enabled by ground command or another onboard app. The period is the number of times the activity is sampled before the execution occurs. In this case, it executes every cycle. For an activity with a period greater than 1, you can actually skew the execution across seconds. The last field is an index into the message table that indicates which messages to send. The message table is an array of CCSDS messages, so scheduler literally sends the message table entry on the software bus when an activity executes. Here we see LC's messages in the message table. Index 17 is the execution message, and index 16 is LC's request to send its housekeeping telemetry packet. Most messages don't have parameters, but here we see LC does, and it can use these parameters to affect its execution. Conceptually, Kit Scheduler's tables are very similar to the NASA Goddard Scheduler app's tables, so this information I've presented will help you if you're using that app. I've launched the Scheduler TO table demo script from the Runtime app screen using this button. This started the script runner, which is shown here, and I've already started the script, and it's now displayed 2 windows. The Manage App Runtime screen, which we've seen before, and we'll mostly be interested in this top part, which is telemetry packets. And it's also started the Autonomy Management screen, which is over here. This screen displays the stored command status and the limit checker app status. You don't have to worry about most of these information. We're really interested just in the limit checker app. So the app state is disabled and the action point sample count is 0. And here's the CFS terminal window. So when I hit go, well, before I hit go, let's review quickly the limit checker messages. So in the app definition, here's our send housekeeping request, our sample action point, which is also known as execution, and then this is the actual housekeeping telemetry message ID. So in the scheduler message table, at index 16, we have send housekeeping. Index 17 is the execution. Scheduler table is slot 1, entry 0, activity 0 is execution, which indexes into the 17, and 2 and 14 is the housekeeping. And finally on the back end is a TO packet table, and right now the default configuration is send 1 of 1, or every packet. So now when I hit go, we're just going to display some of the information. And so this is message table index 17, and I sent the message table entry command, and this command also looks into the scheduler table to find the first entry that's using that message ID. So it found slot 0 activity, and it is false. So now we're going to set the limit checker to passive mode. We see it turns to passive, and we still see the counts 0. So passive mode means limit checker is now activated or will respond to the execution command, but it's not going to take action on them. So the next step is we're going to change the scheduler table to enable to true. And I've also resent that message. So now we see it goes to true, and we see that the sample count is incrementing. And if it's incrementing by 4, because right now limit checker is set up to have one action point, so it's sampling one action point, but the housekeeping request is coming out every 4 seconds. So it's sampling it every second, but then it's being reported every 4 seconds because of the scheduler table. Now we're going to change limit checker's housekeeping request to once every second. And as you notice, it's now incrementing every second. And we can also, okay, so now we notice it's every second. Next, we're going to show TO's packet entry for the housekeeping. Because we actually haven't, that was in the comments before. So now I'm going to show it, and we see it is 1 of 1, as we expected. Now we're going to change TO's packet filter to be 1 of 4. So the execution's happening once a second, and the housekeeping is being reported once a second, or requested once a second. So now we're going to change it on the back end, which is the telemetry output filter table, and we should see it now slow down again to 1 of every 4. So 71 to 75. So how are we doing so far, David?
I want mommy.
To summarize, here are the steps for integrating an app's messages with the OpenSatKit runtime environment. First, define the message IDs in the app's message ID header file. Second, add the necessary message definitions in the scheduler table's message file and configure the scheduler table for when to send the messages. Third, add the app's messages to KitTO's packet table for the ones you want to go down to the ground. And fourth, define the Cosmos command and telemetry files. Here are the message definition file locations. Each app has a platform include subdirectory that contains the message ID header file. OSK defs is the location of the default JSON tables used by the CMake build system. On the ground side, a single Ruby file, flight software message ID.rb, defines all of the message IDs, and these are referenced by the Cosmos target definition files. It's currently a manual process to keep the files in sync, but the long-term OpenSatKit goal is to define the messages in a single location and automatically generate any dependent files and artifacts. Now we're going to consider the bigger challenge of designing a complete scheduler-based system. First, what are the hard real-time requirements? They're often driven by the attitude determination and control and guidance navigation and controller frequencies. Also, the payload control and data management cycles are usually high priority. Next, what control and data flows are involved with the real-time requirements? What are the hardware devices and how do they interface with the processor? Does the scheduler app need to coordinate I/O? Some architectures use a distributed 1 Hz timing pulse to synchronize the processor with sensors, actuators, and payloads. Since the scheduler app can be synchronized to the 1 Hz timing pulse, it can be used to manage a synchronous system. Next are the relative hardware timing requirements. For example, a rate measurement may need to be correlated to a star tracker measurement, so you got to make sure you know the timing between those two samplings in a deterministic way. What apps require scheduled messages? Also, are there optimal relative timings between apps? For example, limit checker may run on a cycle after the controller, so that way it can take action on a illegal state or some error condition that was determined by the controller app. And finally, after the initial system is designed and prototyped, it can be measured and tuned. And remember, this is an iterative process, especially if the hardware design and interfaces are being defined in parallel with the flight software system. This table identifies main loop control mechanisms for each of the OSK apps. From a control loop perspective, they can roughly be divided into 2 groups, scheduled and data-driven. Most of the scheduled apps pen forever and execute when they receive a scheduler wake-up message or send a housekeeping message. For example, CFDP, CCSDS File Delivery Protocol, is a scheduled app that's often scheduled very frequently so it can keep the file transfer up with the data rate. And we've also taken a look at the limit checker app, and it also is a scheduled wake-up. Data-driven apps typically pen forever or with a timeout and execute when they receive data from either an onboard app or from a ground command. For example, data storage takes packages from the software bus and stores them in files, so it's being driven by the data that it's subscribed to on the bus. File Manager pens forever, but it's really just waiting for a ground command, and occasionally it'll also get its housekeeping request. F42 is the flight software controller, and that's it looks like it's data driven, but in a sense it's pending for the data packet from the Interface 42 app, which is actually a synchronized app with a schedule driven. A third hybrid option that isn't shown is for an app to have two pipes. One can collect data packets, and the other can be used for execution control by pending on a scheduler wake-up or on a data packet whose timing is known relative to the other data packets being collected on the other pipe. Here's the scheduler table for OSK's reference mission called SimSat. OSK is a non-real-time environment, so I'm using 4 slots to keep things simple. This table is designed around a 2 Hz controller operating in slots 0 and slots 2. For a real-time system, you may want more slots to spread out processor loading. Activities within a slot are executed sequentially without any delays, so you need to use slots to separate timing. Stored command is in slot 0 to keep it synced with the 1 Hz, which keeps timestamps close to a 0 subseconds, which seems clean, but in reality the default stored command configuration runs on a 1 Hz schedule, so subsecond granularity is really not that relevant. Limit checker and housekeeping are intentionally scheduled in the slot after the controller, so the most recent data is used. The file transfer app is scheduled in non-control cycles because it can be time-consuming. Finally, the send housekeeping requests are spread out across the slots and can be staggered using offsets if necessary. I'm now going to take a step back and look at the different test environments where the runtime apps will be used. First, there's the Software in a Loop, or SIL, which is a desktop runtime environment typically used for initial app development with interfaces stubbed out or simulated. OpenSatKit is an example of a SIL configuration, and UDP-based CI and TO apps are adequate. Next is a Processor in a Loop, or PIL configuration. A commercial processor card is often used for this configuration, so the UDP-based apps can be used. There are different levels of fidelity regarding interfaces, so some organizations may simulate the flight COM interface, in which case the flight CI and TO will be required. A FlatSat configuration is intended to be as close to the spacecraft as possible and has a hardware COM interface, so the flight CI and TO are required. It's also a good platform for running flight software acceptance tests, so you want all of the apps to be flight apps. The spacecraft integration and test environment and the flight operations environment both must use the flight versions of CI and TO. I would like to mention some test environment considerations in the context of the runtime environment apps. There will be tutorials on verification and validation that will go into more detail, but here are some initial thoughts. State your test objectives. Determine what interfaces and level of fidelity will be needed to meet your objectives in each test environment. Do you need to repeat tests within a single environment? Do you need to reuse tests across environments? Analyze the test environments across the development lifecycle and ensure all necessary tests are being performed in a cost-effective manner that align with the schedule and budget. The runtime apps are configured during the build process for each test and operational environment, and typically don't need much operational reconfiguration. TO's packet table is the one exception. Many missions have different phases that may have different real-time telemetry priorities and different downlink scenarios. Creating and storing multiple TO filter tables on board simplifies this task, and I'll show an example in a minute. These tables should be coordinated with data storage tables that determine which packets are stored and later downlinked as playback data. I've listed configuration commands for each runtime environment app. CI doesn't need configuration, and we've seen many of the TO and scheduler app commands already. Finally, I'd like to point out that NASA's scheduler app has the ability to resync with the 1 Hz pulse and the concept of scheduler groups that can be enabled and disabled. These are very convenient when you have hardware redundancy. I'd like to conclude this tutorial with a demonstration of using TO filter tables for different downlink rates. We'll use a test scheduler table that has 2 housekeeping requests per slot, and all of the housekeeping requests are at 1 Hz. 2 kit TO packet tables are defined. One sends all the packets, and one sends one of every 4 packets. This table shows the expected results. The packets per second and the bytes per second are part of TO's normal housekeeping telemetry. For the 1 Hz case, we expect 8 packets per second and 842 bytes per second. For the quarter hertz case, or 1 packet every 4 seconds, we expect 2 packets per second and about 210 bytes per second. This demo was kept simple to highlight the data rate management and doesn't illustrate the data priority. I've started the TO Stats demo from the Runtime app screen down under the Learn section. The demo script has started in the Cosmos script runner and is waiting after the initial setup. When I click Go, we'll configure the 1 Hz case by loading the scheduler table and the 1 Hz telemetry output table. I also have the Kit TO housekeeping telemetry packet open, and the things we're interested in are the stats valid, packets per second, and the bytes per second. Right now the stats valid is reflected in the default scheduler table and packet table. And I also have the CFS running down here. So I'm selecting Go, and it's going through some initial setup to load the tables. And now it's waiting for the stats valid to turn from false to true. And this will take several seconds because the stats are computed over a running average period. And it's got to wait for that period to cycle through once. The stats valid is true, and now we're waiting at the step to collect and report the 1 second data. So I'm going to go ahead and say Go. And now it's actually going to go through in 3 times and do an average over the samples for 3 updates. And the message box says that our 1 second demo results that were within 100%. So we have 8 packets per second and reported 841 bytes per second. Now we're going to go to configure the 4 second test, or 1 of every 4 seconds. And we'll go ahead and wait for the stats valid to transition from false back to true. We're now back with the stats valid to true, so I can go ahead and hit Go to collect and report the data for the quarter hertz test. As you can see, the quarter hertz demo results, we got 2 packets per second exactly, and we computed 208.3 bytes per second, which is within 1% of the 210 we expected. So this concludes the Runtime app tutorial. Thanks for tuning in.